Your back is broken? I'm sorry. I believe in you, though. You can fix it. So, for starters, we have the world's most stock installation of Windows ever. So stock that the little bar is still in the middle instead of over on the left where it's supposed to be. So let's super duper fix that real fast. AI is going to do a very fast how to learn C++ in one stream. The goal is I want to get through like everything pertinent in about an hour. Can we take bets on whether or not I'm going to meet that goal or not? We're going to start the timer at 6 o'clock. And if I'm not done by 7, you'll get to laugh at me and call me a nerd. Sound good? But we are going to go super duper duper from the beginning. So from the beginning, that we're going to open up a web browser and install Visual Studio. C++ equals my brain soup. The goal is that will not be the case by the end of the stream. So let's go download the community version of Visual Studio, which is Microsoft's beautiful, awesome, 10 out of 10, no complaints at all compiler for Windows. AI is not being sarcastic. What are you talking about? Because I love it so much, we're going to go and download its little brother so that we have a decent environment to work in. So we'll give baby Visual Studio Code a quick download as well for anyone who who's feeling brave enough to try and follow along. And then click all the buttons on the code installer, wait for the big installer to actually start up, and select that we would like to do desktop development with C++ and install all of the components. So what just happened? AI just pushed a ton of buttons and started installing a ton of things. What are they? Well, let's click the final install button. Another installation is in progress, damn it. And let's switch over to our super handy dandy little hi chat message. Isn't it friendly? So what did AI just do? Well, for starters, we installed Visual Studio. What the heck is that? This is what's called a compiler. The compiler's job is to take code, which we're going to spend most of the rest of this talk writing, and to convert it into machine code. So code is what a human likes to read. Machine code is what an AI likes to read. Code winds up looking something like stood, see out, hello world. And then the equivalent machine code for that might look something like 01110100001. So the machine code is optimized for a computer to very quickly process it, whereas the source code is optimized for a human to be able to read and understand. So Visual Studio's job is to take the human readable version and emit the machine readable version. What else do we have? Well, then we installed Visual Studio Code. This is a fancy text editor. We're going to install a couple things inside of it, which will make our life easier for editing code. But all this does is edit text for us. Very, very fun. The last thing we installed was CMake. So CMake's job is to explain what compiler do. So rather than having to issue some commands for the compiler to do its job, CMake will let us write a short little file that will tell the compiler what to do. So with the brief understanding of all the things that are floating around under the way, let's go over to code. The other reason we're grabbing code is so that when I use it later on in not Windows environments, things will look familiar. And we're going to go over to this button on the bottom that says extensions, and we're going to search for Edwin. So bring up a big list, and we're going to find Edwin C++. Install all the C++ extensions. Those will take a second to install, and then once they are done, we are going to restart Visual Studio Code. Cool. Now, we should be able to go to Documents, or wherever, and create a folder, CPP, in OneStream, that we're going to use for the code for today. So we're going to open, great. There was a checkbox that we should have installed when installing Visual Studio Code to give us an open Visual Studio, but we can do it the slightly harder way of opening the big scary terminal and just typing code dot to open code in the current folder. So to get started, we're going to make the world's simplest C++ file. I'm going to call it main.cpp, main.c++, and we're going to write every programmer's first program. Hashtag include, IOStream, int main, stdc out, hello world. So this program includes the standard library for input and output streams, and then uses the console out stream to display the message hello world and then end the line. We're getting some messages down here, so we're going to follow them, just disable IntelliSense, and it'll ask us to reload. And then we're going to make the cmake script to build this tiny little file. So to do that, we're going to make a file called cmake lists.txt. It requires that we tell it the minimum version of cmake to use. So we're going to say cmake minimum required version, and we're going to say that 3.21 is the minimum required version. If you ask for a version too old, it complains. And if you ask for a version too new, it won't be able to run on some computers. So 3.21 is a pretty good number for 2025. Then we're going to simply say add executable. We're going to name it main, and it's going to take the main.cpp file. So this little script will tell the compiler, hey, we're going to use this particular version of cmake, and we're going to make an executable called main. So what just popped up was it noticing that Visual Studio has been installed. So if we come over here, we can pick what's called a kit. So we can select what version of Visual Studio we would like to use to compile, or more accurately, what we're going to target with Visual Studio. x86 is not really used anymore. That's older 32-bit computers. Pretty much every computer these days is a 64-bit computer. So using either the 64-bit or the 64-bit 32-bit version is what everyone winds up using. So we'll pick that we're going to use AMD 64, and this will figure out all the information about the compiler for us, which will take a hot second since it's still finishing up the installation. And like that, with no scuff at all, we can click this little run button down here. We've successfully created our first program, and we've printed hello world to the console. So this is not exactly the world's most interesting program, just printing hello world. Maybe we can print something a little bit more interesting. Like, let's print a nice little greeting for Russell. So let's say auto name equals Russell. And instead of printing hello world, let's print hello name. Any bets as to what this is going to print when we run it? As a side note, Visual Studio will now start up, and we can say skip add accounts later, start it up, and then just close everything. We won't be needing him anymore, just his little brother. And hey, look, we've now said hello to Russell. So an interesting thing here is if we hover over to the right side, there's this little option to add a breakpoint. We click that, and then instead of clicking the play button to run, we click the bug button to debug. Instead of running our executable, it will step through it. So what do I mean by that? Well, we can press the step button to go like the computer and execute one line, and then the next line, and then the next line. Then as we're stepping through, we can look at names that we've created and see what values they have. So like name has the value Russell with some big number, which we'll talk about later. And then we step over the next line, we'll see hello Russell got printed out. Isn't that neat? So the most important thing to start off with here is the idea of a function. So what is a function? A function is a piece of code that can be repeated multiple times. So for example, we can make a little small function here called add. So int add, which takes two values, A and B. We'll talk in a minute about what int means. And then we'll return A plus B. And if instead of saying Russell, if instead we say add 5 and 6, when we run this program, it should print out an error message complaining that the add function doesn't exist. So easy fix for that. We'll just write the add function before where it's used. And now it should no longer complain about the add function not existing. And it should print out the number 11. So what happened here? Well, the return basically means end and bring back the value. Replace yourself with this value. So what are we replacing ourselves with? A and B. So the compiler basically goes in and copy paste this in. But what are the values of A and B? 5 plus 6. But what's 5 plus 6? 11. And if we step through with the debugger, you'll see what happens now using the step into function instead of the step over function is we jump up into add, we do the calculation, and then we return 11, which can then be printed out. Make sense? Any questions so far? Well, the obvious question to ask at this point is, what's an int? So there are a handful of main data types that we use. We have data, but what does it look like? Well, if we're using an int, what do numbers look like? -1, 0, 1, 2, 3. What do we notice about all these numbers? Well, first observation, they can be negative. Second observation, there are no numbers like 5.5 or pi, whatever the heck that means. There's a whole day named about it, but whatever it means, right? So integers are positive and negative numbers that don't have any decimal points. So things like 1, 2, 3, right? If, oh shoot, the undo is, oh, there it goes. If we want to have numbers with decimal points, that's where we start using a float. Float is short for floating point number, and it allows you to start floating a decimal point. So we get numbers like 1. Integers are also floating points. 5.5, we have a decimal, and 1,277.8. So there are other fun things we can use, not just numbers. We can have a stood string. So this is something like Russell, where it's a bunch of characters all combined together. And then let's go and look at another interesting thing that we can have. So we're going to make what's called a variable. So we've already made one. This here is a variable. It's something that has a value and a name, like name, and then can have values assigned to them. So we'll make a new one with auto names equals stood array, stood string 2. Like we just saw, stood strings are multiple characters put together. So like an English sentence would be a string. And now we have an array of 2 strings. What that means is that we can have 2 strings, say Russell and DJ, and we can put them together into this one variable. Now, when I want to access them, I can go names square bracket 0 to get the first one, or names square bracket 1 to get the second one. Why does it start at 0? That seems a little bit weird. The reasoning is that behind the scenes, it's doing math. So it does something like this. What's the first? It's at +0. What's the second? It's at +1. So when we're looking things up in the array, 1 is at subscript, we call them 0. We compile this, it will either work or it will complain that it doesn't know what an array is because we need to include the standard header for it. So now when we run the program, we get Russell printed out again. And if we print out names 1, we should get hello DJ. But what happens if I want to print out both? Well, I can use what's called a for loop. So I can go auto name in names. And now instead of printing out names, I'll print out name. And you notice the way I read this. For auto name in names. If you add the word each in there, for each name in names, what's happening here is very clear. We're going to take each of the things in this list of 2 things, right? Name each of them name, and then run this code for each. Make sense? So I'm using this word auto a bunch. What exactly is an auto? Well, we talked before about int, right? And float. Well, auto just means figure out the type for me. I don't care. If I wanted to, I could instead spell out stood array, stood string 2. But that's quite a bit to type, right? So rather than doing that, we're just going to say auto. And likewise, I could spell out stood string, but again, that's a lot to type. So we're just going to say auto. We can do this in a slightly harder to use way, and again, in a even slightly harder to use way. So using a for loop, instead of looping over each thing in an array, we can run some arbitrary code on like a list of numbers. So we can make an int. We're going to name it index, and we'll start at 0, where arrays start. And then we will continue while index is less than names.size. So we're going to go in and ask names how big it is, and we're going to loop less than that. If we were to be a little bit more specific, we could say less than 2. But then if we resize this array, it would break. And then we can say index equals index plus 1. So we're now introducing this new idea to variables, right? I'm performing some computation and then storing the results in a variable. It's also worth noting that unlike in math, we can have a variable equal to itself with some modification. This just becomes a value, right? At the very start of the program, it's going to be 0. So 0 plus 1 evaluates to 1. Now index is 1. Second time through the program, index will be run. 1 plus 1 is 2. So now index is 2. Very logical. So let's run this. And we should get an error because name no longer exists. Instead, we would have to say names index. So name 0, names 1, and so on. And it should print out the same thing as before. But now, when we run the program through the debugger and step through, we'll see that index has the value 0. We print it out. And then on the next line, index has the value 1. And we print it out. Make sense? So I'm going to create what's called a comment. This is only for humans. The compiler will completely ignore what I just wrote with the slashes in front of it. This is only for aiding human understanding. But what is a for? It has 3 parts. It has a start, it has a check, and it has an update. So at the start of the for, this code will run. Every time we go through, it'll check this, and it will only keep going for as long as this is true. So is 0 less than 2? Yes. So we keep going. Is 1 less than 2? Yes. So we keep going. And then at the end of every time through the loop, it will do this. So we'll do index equals index plus 1. If we wanted to, there is another loop construct called a while loop, which we could use. A while loop only has the check. So while check. So we could write index is less than 2 and post our code in. And if we try to compile this, we should get a little error. It will tell us, hey, look, index is undeclared. It doesn't exist. So we need to tell it, like we did here, that index exists. That should now fix this error. But when we run it, we get hello Russell repeated for over and over and over forever ad nauseum. That's because this bit of code that updated the index never ran. So if we see what's happening here, we run index is 0, index is 0, index is 0. There's no code to tell us to update what the index is. So instead of running one line of code inside the while loop, we're going to wrap a few couple of lines in brackets, open and curly braces, technically, which tells the compiler, hey, everything inside of these, I would like to run every time the while loop says true. So what else are we going to run? We're going to run index equals index plus 1. If we run that, we should have the exact same behavior that we had before. We have hello Russell, hello DJ. So a for loop is really just a while loop that runs a bit of code before and a little bit of code at the end of every time through the loop, if that makes sense. How is this useful? Why don't we just use fors? And why don't we just use like the nicer version of for, where we just loop over everything in an array? Well, when you're making something like a game, you want to be able to create a whole bunch of frames, right? Every image you show to the player needs to be its own iteration through a loop. So we might have some loop that looks something like this. We set up game, so like load textures, load models, stuff like that. And then, while true, we render the game. And then this loop will keep running forever and ever, giving the player more frames and hopefully doing something cool. This is a game. How does that make you guys feel? Pretty simple, right? In reality, there would be something a little bit more complicated here, like window dot should close, but we want the opposite. So something like this. So this is going to bring us into our next topic about making decisions. So we've seen the while loop, which takes some code and repeats it until its condition is true. But what happens if we only want to run the code once? Something like if player.health is less than 0, die. We don't want the player to die repeatedly, right? We only want it to happen once. Hence, we use this if statement. If a while loop, every time the player's health is less than 0, we die. It repeats until the condition becomes false. With an if statement, no matter how many times, it doesn't even consider it more than once. No matter what happens, it will only check this once. If it's true, it runs this code. If not, it just skips over on to the next thing. But what happens if we want to do something else? Well, we can say else, live. Does that make sense? So it is possible to do nested if statements. So instead of saying else live, we can ask another question. If player.health is less than 5, we can tell them consider healing. And otherwise, maybe we tell them healthy. Make sense? So what can we use to ask questions? Well, so far, we've seen the less than sign. If there's a less than sign, it implies that there's a greater than sign. There's a little trick with these two symbols. The arrow points at the smaller thing. So for less than, right? The arrow is pointing at health. And so we want to ask if health is smaller than 0 or less than. We also have equals. Why is equals 2 equals put next to each other? Well, when we saw earlier, right? Index equals index plus 1. This is a single equals. When we use a single equals, that's what we call assignment. So a little note up here. Equals is assignment. That means take the thing on the right and stuff it in the variable on the left. If we want to check if two things are equal, we need to use an extra equal sign. Turns out we wind up using assignment a lot more than we do checking if things are equal. So we gave the shorter symbol to the more common operation. What happens if we want to check if things aren't equal? Well, the exclamation point means not in computer science, so not equal. And if we want to be very fancy, there are versions of less than equal and greater than or equal. Cool. But what happens if we want to ask more complicated questions? So if we wanted to ask something like, if the player's health is less than 5, and if the day is Tuesday, and if the weather is raining, well, now we're all these layers deep in the if statements, right? That's kind of awkward. Instead, we can use and. So instead of having to list all these if statements, we can check and. So 2 ampersands together means and. Logically, that means that there would also be or. So 2 pipes. The key right above the enter on an American keyboard means or. And then we already mentioned that the exclamation point means not. So we could take all of this and we can negate it. So now we're asking if the player's health is less than 5 and day is Tuesday and weather is raining, not. So not all those things. So the player's health has to be greater than 5. The day has to not be Tuesday, or the weather has to be raining. Has to not be raining. Make sense? Would you believe me if AI told you in what is the timer? 40 minutes, I taught you one entire programming language. You now know pretty much everything there is to know about how to read the C programming language with what I just taught you. But I promised that I was going to teach C++ today. So what are some of the plus plus things that we can get on top of C? Well, let's get rid of a little add function here. You know how we were doing player dot? Well, let's define a player. So we're going to make a struct called player. This stands for structure. So we have a structure, and a structure allows us to group multiple variables together. So what variables might be useful to a player? Well, we're talking about their health. So let's say in health. They might have maybe a string for a name. They might have a std array of some item struct. So we're going to say that a struct called item exists, but we're not going to define it. And maybe they can have 10 things in their inventory. And now in main, we can make a player called player. And then we can set the player's health equal to 5. Will it complain about this? Yes. So let's make an empty struct called item. So weird, how should I say, pain point in C++. Most blocks, so things between curly braces, do not need a semicolon at the end. Structs do. That is due to a legacy feature from C, where you are able to make variables of the struct type inline. This is used very rarely nowadays, but it's still there. One of the nice and not nice things about C++ is that it tries very hard to be backwards compatible with C. So if you have C code that was written back in the 70s, you should theoretically be able to compile it with a modern C++ compiler, and it should work. Theoretically. Downside, we got a lot of weird old features that are kind of painful, and we just have to put up with. Like this, the semicolon at the end of structs. This should build, and then we should be able to print out the player's health. Maybe. There we go. So we were able to just make our own struct. This player struct is kind of an example, right? How about something a little bit more useful? So let's make our own array. So we're going to make a struct array, which inherits from std array. We'll be able to store ints, and we can store 5 of them. What might be something useful that we'd like to do with an array? Maybe we want to be able to add to arrays. So array, add, array, other. So we have a function here. We can add functions inside of structures. So we can pack variables and functions together. And if we write a function inside of a struct, we get this extra variable out of the aether called this. This is the struct. So if I make another function, void means this function does not return anything. Print takes no parameters. We still have this. We should be able to std out, star this, 0. And if we make an array, A, and set A0 to 5, and then call print on A, and let's not do 5 since there's a bunch of 5s in the terminal. Let's put 10. When we run this, we should see a 10 printed out. I completely glossed over what the heck this star stuff means. We will come back to it in a second. But for right now, just know that if we want to access this, we need to wrap it in this star. But more importantly, right, we've now seen that this is this, right? Very logically named. This is A. It's whatever instance, copy, object of this struct, whatever word you want to use, we're currently inside of. So what if we want to add? Well, we could go for int I equals 0, I is less than size. We have access to all the functions that array has since we did this colon thing to inherit from it. We are an array, a std array. Array has everything that std array has, including its size function. If we wanted to be more explicit, we could say this size or this size. But if we want to use all of the variables and functions in the current struct, we don't have to mention this. The compiler is smart enough to add that in for us. We have to do less type it. And then I equals I plus 1. And now what we can do is we can say there's some new array out, and out I equals star this I plus other I. And now if we make an array A, which should be 1, 2, 3, 4, and we make another array P equals 5, 6, 7, 8, and then we make print a little bit better. So it does the same thing. For I equals 0, I is less than size, I equals I plus 1, and we print out the ith item. Now, if we go array A plus B equals A dot add B, and then we go A plus B dot print, what should this be? 6, 8, 9, 12? We didn't write the code to do that. So A0 equals 1, A1 equals 2, A2 equals 3, A3 equals 4. Do the same thing real fast. Well, do the same thing real fast. B, G, B, B, 5, 6, 7, 8. Oh, and it would help if we returned the output value that we made. There is no scuff in the creation of this stream. And like we expected, we got 6, 8, 10, 12. 6, 8, 10, 12. Cool. But an array of 5 integers isn't exactly helpful, right? Especially when we only give it 4 integers, and then it gives us some extra random weird value at the end, you know? So how can we make this a little bit more useful? Well, we can turn our array into what's called a template. So if we write template before it, we can now define a couple more variables, including type names. So in the rest of the language, you're not allowed to write a type, but in templates, you are allowed to write a type as a variable. So we're going to make a variable t whose type is some other type. And then we're going to use int size. Now, instead of having an array of int 5, we're going to have an array of t size. Now, when we make our arrays, we have to specify that t is an int and size is 4, since we're only filling in 4 things. So int 4. And this array should hopefully be smart enough to identify its type from the add. Or not. So we're just going to use auto, so we don't have to type as much. And now we have the exact same thing without the extra 5th element we didn't specify a number for. Make sense? So this template thing allows us to create our own types that can be parameterized on like other types and sizes and stuff. So everything we've done so far has been on what's called the stack. And I'm going to show you a quick little example that shows something funny about the stack. We're going to make a void function called add2, which is going to take nothing. It's going to create an int variable, top, and then we're going to set top equal to top plus 1. I'm going to show you the trick now. Since we obviously write this top equals top plus 1 so often, right? Surely there's an easier way to write it. And there is. If instead we write top plus equals 1, the plus equals expands out to this equals plus thing. So these 2 lines of code are equivalent. You notice I wrote this very specifically. I didn't assign top a value. And now if we, in another function, set to int top, top equals 0, and then if we call another function void print to int top, and then we're going to print out top. If we now call these functions in sequence, set to, add to, and print to, what you would expect to see is that we print out random garbage, just some number. You don't know what number, but nothing useful. But what you'll actually see happen is that the Windows version of C++ is smart enough to figure out that this is a bug and complain about it. Damn. Well, that would have been good to know before I did this bit of demo. Quick check. If we switch to release mode, where we want to go fast, and we have a bunch of the checks turned off, will it do the thing then? Kinda. If we quickly go over to the Linux side, demo.cpp, and what do we have? And if we compile this version, you should see that 1 is printed out. Why is there a 1? Well, if we compile this in debug mode and open up the debugger, break on line 20, and then step into here, and we're going to print out top. Or more specifically, we're going to print the memory address of top, 0x7FFU14. Keep that number in your mind. We're going to go next, step into add to, and we're going to print, we're going to print the memory address of top. Is anyone else sussed out by the fact that it's the same number? We don't quite understand what a memory address is yet, but it's the same number. Is anyone else suspicious? Some suspicious behavior is happening here. Step into print, check the same thing again. What's the memory address of top? So what's actually happening here? So by default in C++, variables go on what's called a stack. But imagine a set of plates stacked on top of each other at like a buffet. So we wind up with the same thing, but with functions. So on the bottom of the stack, we're going to have the main function. And what's in here? Any variables we make. So the player variable that we made earlier will be in here. So what do we observe? We're going to call the set_to function. And what variable does it have? Top. And top is right here. So now we're going to return, and this whole bit of memory is going to disappear. It's just going to pop away, and we're now looking back at the memory of the main function. So now we're going to call the add function. But wait, what happened? While trying to be fast, we wound up reusing the same memory. And if we go look at our code again real fast, you notice how we just have an int, an int, an int, all in the same place. So since it's the first int in a function, it all winds up reusing the same memory. It's actually trying to find who asked. Yeah, it doesn't understand. It all winds up reusing the same memory, and so top winds up representing the same variable. There's also an interesting observation here. I mentioned that this number is a memory address. So far, we've been thinking about variables as values. But really, the more accurate way to think about them is a variable is a label for computer memory. So think about a locker room at school. You're assigned locker 5. So you know that you have 5. You can go over to 5. You can open your locker, and you know where it is. The variable top is assigned locker number 0x7FFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFF and it can find the value there. And since all of these variables wind up getting assigned the same locker because C++ is fast and trying to reuse the same memory on the stack, we wind up setting the same value. Obviously, this is terribly unsafe, super buggy, and the Microsoft version is smart enough to tell us that and like error out when we try to run this program. Sound good? The downside is that sometimes some really good programmers are able to use this kind of behavior to do some really weird, wacky stuff that's really fun. So we saw another thing. If I make an int top, we'll say, I can make another type of variable, an int pointer, p, which equals the memory address of top. So what is p? Well, it's an integer, but it's special. It stores another variable. Because we mentioned, right, that variables are just labels for memory addresses. So why can't we just store that memory address? Locker number 5 as in like some integer, right? And then since we have the reference to locker number 5, we can access P and treat it as if it was top. So when we print out this now, let's not use the 5 again, 21. When we print out this, top has the value 21 because we took its memory address, its locker label, gave it to some other variable to hold. So we told our best friend what our locker number is, and then they were able to go in and find our locker and she messed with it. Make sense? So, interesting problem. When you're putting things on the stack, when a function ends, right, all the memory that was used by that function is basically lost. As soon as another function gets called, it probably overwrites it with its own stuff. So what happens when we want to have a large amount of stuff that exists between a whole bunch of calls to the function? Well, that's where the heap comes in. So the heap is a completely separate section of memory, and we can ask for a little block of that to be assigned, and we can be handed back a pointer into that block. How can we do that? Well, we can go int pointer on heap equals new int. And now when we set on heap equal to, Leo has a 6 in his name, so we're going to say 6. Then we can print out on heap, and we should get a 6. Does anybody else notice that the symbol that we use to access a pointer, what we call dereference? So follow the pointer, go like, ooh, I want to change the value that's actually here. I don't want to change the value here that's pointing. I want to change the pointed to value. Is this little ampersand, asterisk, sorry. Do you notice that we use that little asterisk when we were using the this variable? So this is actually a pointer to ourselves. What's the relevance of that? Well, if it was just a variable, right, we can modify it in this function, and then it would disappear. It would get knocked off the stack, right? We go like, boop, get out of here. But since it's a pointer, it can actually exist in main, right? And then point to what's existing in main. Just like this is pointing to something that exists somewhere else. And yeah, downside of using the heap is the computer has to do a little bit more management, more bookkeeping to track things that exist on the heap. And you have to manually delete them. The fact that you have to manually delete them is like one of the biggest bugs that people forget to do. Like, this is what we call a memory leak. If this doesn't exist, it's a memory leak. And like, there's stories about old versions of Microsoft Excel, like just crashing after a week. That's because Excel had a memory leak where they would make memory and then they'd make some more and make some more, and they never let go of it. And after they made enough new memory, poof, it's all gone. We ran out on the system, and so the whole system crashes. So don't do that. What we suggest is to never actually use new. Instead, include the memory library and create a std make unique pointer of an int. This will work exactly the same, but it deletes the created memory when we're done. Make unique pointer. What is it called? It's just called make unique. There is no scuff involved in the creation of this stream. And for this unique pointer, we have to use the get function instead of the asterisks. Just so it's a little bit quirky and silly. So we're going to move on from this kind of weird heap concept. And we're going to talk about moving versus copying. But before that, we're going to introduce a new type. So earlier, we saw the std array of std string 2, right? Russell and DJ. And then we can loop over each name in names and greet them. Hello, name. We're going to add a little point here about having to be precise. The computer does exactly what you tell it to do. So if I don't tell it to print a space, then it doesn't print a space. But if I do tell it to print a space, then it does. So we just have to be a little bit careful. But now, what happens if I want to add Leo? Well, it's going to be upset because I said that there's 2 things, but then I gave it 3. But what happens if I don't know ahead of time that there's 3 things? So instead of using a std array, we can use a std vector. It works almost exactly the same. However, we don't have to tell it the size, but we do have to include its memory, its library. And we can even add Leo on after the fact. So we can make the variable and then we can names push back Leo. So why did we bring this up now instead of earlier when it would have been more useful? Well, because std array, let's clear out all the garbage here. Std array is on the stack. Std vector is on the heap. So that means that a std array is just a little block that exists somewhere on the stack. We'll make blue array. And then the orange vector is just a little pointer that points to some memory allocated out on the heap. What is the problem with this? If I decide that I'm going to make a copy of this array, right? No issue. We just copy it. If I decide I'm going to make a copy of this vector, well, we get a copy of the pointer, which points to the same thing. And so now if I change the copy here, changing the copy doesn't affect the original. But changing the copy here does affect the original because it's really just a pointer to this thing. Does that make sense? So we have to be a little bit careful when we're using a vector. We start having to think about moving and copying. So if I have a new vector here, which we're going to call names2, which is equal to names, and then I said names2, 0 is going to be len. Nothing should change. But if I move names, do you notice something's changed? Instead of names storing these three things, it stores nothing. Its whole value has been moved into names2. That's because std vector does a bunch of fancy stuff behind the scenes to move for us. What happens if we make the much less interesting version, where we make auto names equals new std string array 3 and set it equal to these three names? Well, first order of business, we're going to have to use the clunkier number looping method. So for int I equals 0, I is less than 3 plus I. Earlier we mentioned I plus equals 1. Turns out that that is so common. So we have I equals I plus 1. We have I plus equals 1. And specifically adding 1 is so common that we got an operator to do just that. 2 pluses adds 1. Programmers are lazy. We have lots of things to do the same thing to make our typing less. So now if we do names I, we'll get the list of 3 names. But now if we go auto names 2 equals names, and then names2 0 equals len, names got changed. So what we've done here is we made a copy. Names and names2 are just pointers, right? We don't have the extra machinery the vector has to move it. So even if we std move, we'll still wind up with a similar behavior because all we can do is copy the pointer. Does that make a little bit of sense? Vector does some extra stuff for us so that when we move it, instead of the pointer, the old pointer still existing, just the new thing has the new pointer. But that also introduces a bit of a new idea, the idea of a lifetime. So normally a variable starts existing. Actually, let's keep this around. Normally a variable starts existing when it's created and it stops existing at the next closing curly brace. So names born, names dies. But when we put something on the heap, starts existing, names born, and then it never dies unless we explicitly delete it. But what happens if we have the vector and we std move it into names2? Well, names' lifetime now ends here. All the values that were in names are now in names2. And now we no longer care about where names lives. We care about where names2 lives. Does that make sense? It turns out that thinking about all this stuff is kind of hard and nobody really wants to do it. So instead, we've created this idea of a view. So normally we have a vector, which is called an owning variable. Vector owns these 3 names. It's responsible for their lifetime. They die when it dies. Okay? But what happens if I want to have a names view? We're going to need to include span for this. And that is a std span of std strings of names. We can use names view, spell it right, names view, the same. We can still loop over it. We can still index into it. We're complaining about C++ version issue here. So I'm going to go target, set target properties, main properties, and then I would like to set the CXX standard property to 20. The compiler error I just got, comment this out and build again. The compiler error I just got is complaining that span is only available in C++20. So I'm going to tell the compiler that I'm going to use C++20. And you notice we have the same behavior. But view, right, is a separate variable from names view. It's just a view. We're able to look at names, but it doesn't own. So what we do is we create all the things that we want to own somewhere high up, and then we just manage views to those things. So we know what owns. We don't pass around ownership. We don't worry about that stuff. Just main owns everything, usually. Or like some really high up function. And then we have a view that looks at names. So there are a couple of different types of views. If we want to have a std array or a std vector, its view is std span. If we have a std string, its view is std string view. Very creatively named. If we want to have like an int or a float or other basic variables, it's viewed by a reference. So what the heck does that mean? Let's write a really simple little swap function. So void swap. It's going to take an int a, an int b, and swap them. Let's comment out all this. We're going to make int a equals 5, int b equals 7, and then we're going to swap a, b, and then we're going to std cout a equals a. Remember the extra colon. Std cout b equals b. And nothing should happen. We should have a equals 5, b equals 7, because our swap function does nothing. So let's add int temp equals a, int b, a equals b, b equals temp. So we need to store a somewhere else, override it with b, and then we can overwrite b with the thing we stored somewhere else. Very basic swap function. And nothing changed. That's because these variables only exist inside swap. So they go on the stack, we swap them around, and then they poof out of existence. We create swap, we create a, we create b, we create temp, then swap ends, and it all poofs out of existence, right? What we instead want is we want a view to these variables in main. How do we get a view to an int variable? Make it a reference. So the ampersand makes this a view. So now, instead of getting a copy of the variables, we're going to look at the variables that exist in main. Works very similarly to the idea of a pointer. In fact, what I would do, the way I would represent this, is I would draw the same type of arrow that I would with a pointer. It would point to something in main. But a view isn't like a number you store, right? It's actually another variable. So it doesn't have any different semantics like pointers do. Because at the end of the day, a pointer is just an integer. But you can use the dereference operator to look at the memory address it stores. A view to an int is an int. A view to a player is a player. A string view to a string is the string, if that makes sense. We don't have the extra integer stuff on top of it. And now, since we're using a view, when we run this function, we should see that a is, Kodoko. We should see that a is 7 and b is 5. Because instead of taking a copy of the variables, we've viewed the ones that exist in main. Also, for the record, these don't have to, like the names don't matter. These can be named something completely different. The names inside of a function have nothing to do with the names outside of a function. Very important thing that a lot of newbies gets caught up on. Would you guys believe me if I told you that there's only one more topic I have left to talk about? And then you guys should know how to read at a high level basically everything there is about programming in C++. Would you believe me if I told you that? That one new thing is pretty simple, but also a little bit hard to wrap your head around. We're going to talk about an enum. So we're going to create an enum called flags. We're going to have one for alive. We're going to have one for dead. We're going to have one for dying. We're going to have one for hooked. This is the enum for the player state in Dead by Daylight. But what is an enum? Enum is short for enumeration. An enumeration is a listing of all the things, right? I think that name maps the idea a bit worse than like structure does. But what we've done is we've listed all the things that this variable can be. So if we have a variable flag, it can be alive or it can be dead, but it can't really be a, right? Does that make sense? Or more specifically, it can be flags alive. And then we're able to do the Dead by Daylight player state is not a great example of what I'm about to talk about next. So we're gonna do a more simple player state. So the player can be moving, they can be in air, they can be jumping, or they can be attacking in like a Mario or a Metroid type game, or they can be dead. But what happens if I want the player to be jumping and attacking at the same time? Well, then I say that the player is jumping and attacking. So observation, when dealing with true and false, we double. So and is and, or is or. When dealing with bits, don't double. And is single, or is single. You end up using these a lot more. Flags are like the only place bit checking happens nowadays. And what do I mean by bit checking? Well, what I'm going to do is I'm going to set move equal to 1 shifted over 1. I'm going to set in air equal to 1 shifted over 2. I'm going to set jumping equal to 1 shifted over 3. I'm going to set attacking equal to 1 shifted over 4. And dead equal to 1 shifted over 5. What the heck does 1 shifted over 1 mean? Any idea? Well, behind the scenes, everything is a series of ones and zeros. So, for instance, the number 1 is the number 1. Who would have guessed? But the number 2 is the number 1, 0. The number 3 is the number 1, 1. The number 4 is the number 1, 0, 0. Observation. What happens if I shift the 1 over? I add an extra 0. So 1 shifted over 0 is 1, is 1. 1 shifted over 1 is 1, 0, is 2. 1 shifted over 2 is 1, 0, 0, is 4. The next one, 1 shifted over 3 is 8. 1 shifted over 4 is 16. Notice that we're multiplying by 2 every time. What we're doing here is we're taking the third bit, and we're ORing it with the fourth bit. What does that mean? That means that we're going to take the third bit, so 0, 1, 0, 0, and we're going to OR it with the fourth bit, 1, 0, 0, 0. And what does that mean? 1 or 0 is 1. 1 or 0 is 1. 0 or 0 is 0. 0 or 0 is 0. So we've taken the state and we've now set both the jumping, and the attacking bits to 1. I bring this up very briefly in passing at the end because in graphics programming, which is what I'd like to talk about next stream, we do wind up using flags. Well, not necessarily a ton, but we use them. So it's something that I need to be able to have people know about a little bit. So in just over an hour and a half, I blitzed through every topic that's relevant in computer science, in C++ to making games. Did I teach all of C++ in the past hour and a half? No. Did I teach the majority of it that people would actually use? Yes, with an asterisk. You know the majority of useful C++ syntax. What do I mean syntax? I mean the human readable stuff. The hard part now is knowing what does a vector have. Like we've seen that we can call the size function on it, but what else can it do? If you look at the C++ reference for a vector, we see that we can check if it's empty, we can push things back, we can erase things, we can swap things, we can compare things. And this is in the vector header, which defines a bunch of extra stuff on top of just the vector. This is in the containers library, which has arrays, vectors, hives, forward lists, sets, stacks, some views, which we talked about. So the easy part is knowing the syntax, right? The hard part is knowing all the functions that exist. And I unfortunately cannot talk about that in only an hour and a half. That's the part that people get cool college degrees learning. But it turns out just knowing how to read code is actually really easy if you know how to read English. There's a very small delta on top of what English uses and what code uses. And good programmers use lots of English words that explain themselves. So hopefully off of this video, you'll be able to read a bit of code.